Hi friends, let's evaluate the retrieval performance of an embedding model in a RAG application. And then we test a bunch of open source embedding models to find out the best performing model. Here we have a very basic RAG solution. During the build phase, we take all our knowledge base, which is in the form of documents. We chunk the documents into smaller pieces, and then we use an embedding model to create embeddings for each of these chunks, and then we store all the chunks along with the corresponding embeddings in this vector store. That's during the build phase. Now, during the usage phase, the user asks a query. We use the same embedding model to create embeddings for the user query, and then we do semantic search on this vector store to retrieve the documents which are relevant to the user query. Once we retrieve the documents, we use another LLM called generator. So to this LLM, in addition to the user query, we supply the retrieved documents to generate the final response. The reason why we are doing all this is because, let's say we have a 1000-page product manual. Now the user asks about a particular feature which is described in a couple of pages. Now, instead of giving all 1000 pages manual to the LLM and asking a question, what we want to do is we want to find out the relevant context from the 1000 pages and give only that to the LLM. There are a bunch of reasons why we do that. The first one, we want to make the job of this generator LLM easier. If we give all 1000 pages, the LLM might not be able to find out where in these 1000 pages the relevant context is. And by narrowing it down to few chunks, one, we are making the job of the generator LLM easier, and then the LLM will be processing a fewer tokens instead of all 1000 pages, right? Let's say we are providing only a couple of pages. And finally, so that reduces the cost, and since it is parsing only a couple of pages as against 1000 pages, the latency will also be reduced a lot. Okay, so it will be quicker, cheaper, and also the LLM jobs becomes easier, and that will avoid the hallucinations as well when we provide the right context. All right. Now, once we provide the right context, any LLM does a decent job of generating a decent answer. Now, within this system, there are two models. As you can see, we have a retriever and we have a generator. Now, as I mentioned, once the retriever does its job well, any basic LLM does a very decent job of generating the answer based on the provided context. The retriever model is more complex. The reason is, as I said, in this 1000 pages, it has to figure out which are the 3 or 4 documents relevant to the user query. So the embedding model is much more important in a RAG application. All right. Now, let's see, we build a RAG application. Now, how do we evaluate it? And then how do we find out the best model? So today we look at a method which involves a ground truth. All right. So the ground truth, that's the language generally used in machine learning applications, which essentially means we know for a given input what's the right output. Okay. So once we know that, we test the system For a given input, we have the output and we compare that against the actual output. That's basically the idea. Now, how do we do that in a RAG context? So what we do is, our knowledge base, we divide it into multiple chunks, right? For example, let's say we divide it into 1000 chunks, 1000 pages into 1000 chunks. Now, this is a manual process. Of course, we can leverage LLMs as well. We give the context to an LLM or a human, and we ask them to create a question which can be answered using that context only. Okay. Again, we can give all this to an LLM to generate a question, but we only need a couple of dozens of the data to test. So in my experience, it's a good practice that we create the ground truth manually instead of using another LLM, right? So from those 1000 pages, we pick, let's say, 20 pages, which are very information rich. So for each page, we manually create a question which can be answered only using that particular chunk / page. Okay. So we create these pairs. A couple of dozen would be more than enough. All right. So the ground truth in this case is, we have the context and the question pairs. They are mapped, meaning that question can be answered using the context. Okay. And in the next video, we will see a method without having this ground truth. All right. Okay. For this exercise, we will use this dataset called RAG dataset, which has these 12,000 samples. Okay. So this dataset has these three variables. We have the context, we have the question, and then the LLM generated response. Okay. So we provide this context and we ask this question to an LLM, and here is the answer. Now for this exercise, the answer is not relevant because we are assessing the performance of a retriever. So only the question and the context are relevant to us. Now, for a real world scenario, all these contexts will be relevant. For example, as I mentioned, the product, right? So all 1000 pages are relevant to that product. Maybe we have policy documents. So the full knowledge base is relevant to a particular topic. Whereas this data set is built for testing the RAG applications. So here, each record is on a completely different topic. Just keep that in mind. All right. So let's see how we evaluate, right? A bunch of standard Python libraries, and then we will be using Ollama to access a bunch of embedding models. All right. And then we'll use the load dataset to load the Hugging Face dataset. Here is the same dataset, the RAG dataset with 12,000 records. It's saved as train and test. If you see here. So out of those 12,000, 9,600 records are trained, 2,400 records are test. So let's access all the data. All right. So here we have the context and the question, which can be answered using the context, and the answer is not relevant for this exercise. So let's pick a random record. So here we have the context. This is all the context. And then here is a question which can be answered using this context. All right. So here we have some renewal program from some hospital. So as you can see, the question is, what is unique about this renewal program at Brookhaven Hospital? As you can see, they help the patients with different sort of disorders, etc. right? So that question can be answered using this context. All right. Now, unlike the language models, which have thousands of tokens context window, the embedding models typically have a few hundreds to max a few thousand. Okay. Now, some of these contexts in this data set are really, really long. So the embedding models we are going to test, the lowest context is only about 500 tokens. So what we want to do is we want to count how many tokens are within each context, and we want to filter out the larger ones. Okay. So just a helper function using tick token, we can count the number of tokens in each context. So we applied. So all we did is figured out how many tokens each of these contexts have. Okay. For example, the first one, it has 678 tokens, the second one 943, etc. All right. Now, some of the questions are just empty. So just filter that out. And then just to be on the safe side, we are selecting or we are filtering out all the records which have the number of tokens more than 450. All right. And then to test the application or the embedding model, we don't really need 12,000 records. That will take quite a lot of time. So here we are randomly sampling 1,000 records. Okay. As I said, in a real world scenario, even a couple of dozen are enough. So from your knowledge base, pick up maybe 20 or 30 chunks which are very information rich, and for them map out questions. All right. So we have the context, we have the corresponding question, just saving the dataset. And today we are going to test these 7 embedding models. Now these are the most common used embedding open source embedding models, and also these are the most downloaded ones from Olama. The Nomic, this is from Atlas. They develop nice embeddings related, the embeddings visualization related products. Now this is Mixedbread. That's one of the top companies for developing embedding models. The Gina one. And then we have all MinLM. That's the smallest embedding model from Microsoft. And then we have Snowflake. And this BGE, that's from Beijing Academy of AI. And finally, we have the Granite model. That's one of the recent models from IBM. Now, if you want to test more models, here are some suggestions. Not all of them are available on Olama, but some of them are available on, all of them are available either on Olama plus Hugging Face. Okay, so you can use them for free from Hugging Face. All right, now let's just check the context length, the number of parameters, etc. of these models. So here what we are doing is from Olama show, we can access the metadata. So from this metadata, we are just accessing what's the context length, the embedding size, the parameter size, and the family of each of these 7 models. Now, as I mentioned, this all MinLM from Microsoft, that's the smallest model, which has only 33 million parameters. Okay, and the biggest model is from Snowflake. This has 566 million parameter. Now, typically the LLMs, the ChatGPT LLMs, those have a trillion parameters, and some of the open source ones we see like 7 billion parameters, 70 billion parameters, something like that, right? The Llama models, the Mistral models, things like that. Typically 7 to 70 million, a few hundreds of billion parameters. As you can see, the embedding models are only within these millions. So these are typically 100 to 1000 times smaller models. All right. As I mentioned, the context length, the minimum context length is 512. That's why we have filtered out the records which have the larger context lengths. And the embedding size, these again, it typically be a couple of hundreds to maybe max 1000. All right. So the Snowflake model, again, it has the largest context length of 8,000, and we have a bunch of models. We have 4 models with just 512. All right. Then what we are going to do is we use all these 7 embedding models one by one to build the vector store by running our 1000 chunks. Okay. All right. Just we want to monitor how much time each embedding model is taking, etc. Because that's also important in production when we want a very quick response. All right. So we are looping over all the embedding models, and we are accessing the models using Olama, and then we are using the FAISS from Facebook for our vector store. So with this one command, we are providing all our 1000 contexts, and we are supplying the embedding model. Now this will compute the embeddings for all our contexts. Okay. And then with this, we are just start time, end time. We are simply tracking the time. All right. Just storing some data. And here we are persisting the embeddings and the corresponding documents to a local disk. Okay. So that we can use them later. All right. So here we have the processing times. And now once we run it, what it does is it will create within this folder, it will create a folder for each embedding model. So this is how it looks like. So for the 7 models, we have these 7 folders. Now, if you look any one of the folder, we have this index files. This will contain both the embeddings as well as the corresponding chunks. All right. And then when we want to use, so this is during the build phase, right? So as we saw here, yeah. So what we have done is we did the build phase. So we created the embeddings and we store them in this vector store on our disk. Okay. And then during the usage phase, we load the vector store and from the disk. All right. Okay. So just plotting the processing times. And here we have the processing times for processing 1000 documents for the 7 models. Now let's see how this relates to the size of these models. Now the Snowflake, as we saw, is the largest or the biggest model with 566 million parameters. And this took about 175 seconds for processing 1000 documents, meaning creating embeddings for 1000 documents. Now the smallest model, the MinLM, and a couple of other models which have just around 100 million parameters, these are thrice as fast. So they took only about 50 seconds. All right. Now, what we are going to do is we load the vector store, and then we provide each of the 100 questions, and for each question we retrieve the context. Since we have the ground truth, we can check if the retrieved context matches with the ground truth we have. Okay. So again, as before, we are looping over all the embeddings, and here we are loading the embeddings from our local disk. And in a typical RAG application, we extract the top 5, 10, maybe even 20 documents if we are using re-ranking methods, etc. But in this case, for this data set, we know for each question, there is only one document which is relevant to that question, right? So what we are doing is we are extracting only the top one document, okay, which we will compare with the ground truth a bit later. All right. So we define the retriever. Now here we are going over all the questions one by one, and we invoke the retriever. So we find the relevant context using the vector similarity for each of those questions, and then we are tracking all that information. Okay. Now this is all again time related. So what we have done is we have started with this thing, right? We have started with a question, and this is the ground truth context, right? So we use a bunch of embedding models. Now for each embedding model, we provided the question, and from those 1000 documents or chunks, we have extracted the most relevant one. Okay. For example, when we ask this question, okay, what is the robots product made from? And we have provided these 1000 contexts, and the Nobel embedding model, it has come up with, hey, this as the most relevant context for that particular question. Okay. All right. So we do that for all 7 models, for all 1000 questions. Okay. Now we know for each embedding model, the extracted context, and we already know what's the right context. Now we can compare for each embedding model how many times it actually match with the ground truth. Okay, that's the idea. All right. So again, just the processing times, these are in line with what we saw here. Again, the largest model took at least thrice as much as the smallest model. So if we have a use case where where we require a very minimal latency, then probably we go with the smaller models. All right. Now, okay, now that we have this data set, what we do is, it's a very simple one. All we are doing is, for each embedding model, we are comparing how many retrieved context match with the actual ground truth, and we are simply summing them up. Okay, and then just taking the percentages. So here are the final results. Now, out of 1000 questions, the Snowflake embedding model is able to extract the right context for 941 questions. Okay. Similarly, the MinLM embedding model, it has extracted the right context for 874 questions out of those 1000 questions. All right. If we convert them into percentage, because here we are dividing with simply 1000, it's straightforward. All right. Okay. Let's just plot this one. So here we have the plot. So I'll share all this code in the GitHub. This is just for plotting. Okay. So here we have the final result. And then let's compare that against the model sizes. 1, 2, 3, 4, 5, 6. Okay. We have one more. Okay. All right. So here we have the retrieval accuracy percentage, right? For all the 7 models. Now, okay. So the Snowflake has the highest accuracy. So 94% of the time, it is able to extract or retrieve the right context from the vector store using semantic similarity. Now, as we saw before, among all the 7 models we have used, the Snowflake is the largest one with 566 million parameters. Now, the performance, again, depending on your application, it's not too bad. So at least 6 out of 7 models have retrieval accuracy more than 90%. The MinLM, it's also close to 90%, 87.4. But given its size, which is just 33 million parameters, which is 20, maybe 15 to 17 times smaller model as compared to Snowflake, and which is also at least 3 times faster, right, compared to this model. It still be able to have this 88% retrieval accuracy given how small the model size is. Okay. All right. So the idea is simply creating the ground truth, right? So what you want to do is, once you have all your chunks, pick up maybe 20 to 30 chunks which are information rich, and write down one question for each chunk which can be answered only using that chunk, right? not using other chunks. So be careful which chunks you pick and carefully design these questions. As I said, you need to do this only for maybe 20 to 30 to have a decent, obviously the more you have the better, maybe 100, that's very good. But even with using 20 to 30, you should be able to assess the retrieval performance of your embedding model decently. All right. In the next video, we will see a method where we do not have the ground truth, right? As you know, creating this ground truth is the most manual intensive and the expensive process, right? Now let's say we don't have the ground truth, we don't have the mapping of between these contexts and questions. Then how do we evaluate the retrieval performance? That we will see in the next video. That's all for this video. I hope this content is useful. If it is so, consider sharing within your network. Thank you very much.